Prove mathematically. In fact, I'm gonna do that. It's a long time coming.
Where's my whiteboard? I just blows my mind by the fact that it actually pulls out like the Schrodinger equation.
Oh, it's just writing on the board.
It's written on the board, like, yeah, that's actually right.
I'm gonna prove it mathematically. Smart Sam. He's going.
I feel like when we turn this back on, you should just have a board full of equations and I'm going to question.
Right.
Switch to electrolyte one.
So anyway, since I forgot to turn the tape, or I mean the camera on, yeah, that was complicated, but I'm sure he'll figure it out.
It's not that bad.
Right.
I'm sure you guys can just look at this.
Those were great questions, though. I don't think you wouldn't have understood it if you didn't ask those questions.
Wow, you really opened up my eyes to this subject.
Yeah.
Those questions.
Yeah.
I feel sorry for everybody who didn't get to hear those.
Yeah, it's almost like not seeing a total eclipse.
No.
Too soon, too soon.
Yeah.
We'll just see 80%.
It hurts. Did you get to see this?
I did, as a matter of fact.
It wasn't cloudy?
It was not cloudy. I was like pinching myself. It's actually going to happen.
Did you go to Kentucky?
Yes. Did you see it?
Yeah.
Yeah, did you? Yeah. Where were you?
Like probably 5 minutes southwest of Bowling Green.
Yeah, okay.
Yeah,
Kentucky.
Okay.
I thought for a second, which is where I was, basically.
Oh, really?
Yeah, I was thinking Bowling Green, Ohio.
No, it's Kentucky.
That's not the no, wait, Bowling Green, Kentucky. That's where I was. Actually, I was almost. Yeah, you were near me. Basically.
Oh, really?
Yeah. How long was your totality?
It was, I don't know, maybe like a minute and a half.
Yeah, 94 seconds.
Yeah.
Oh, you're like 3 houses over?
Well, we stopped at the construction site.
Oh, really?
Yeah.
Yeah, we're going to have to go on Google Maps and find it because I was at Professor Qin Shan Wu's, former Chinese professor here, backyard.
Oh.
Yeah.
Yeah, I was in someone's backyard.
What's that?
I was at construction site.
Yeah, but you were probably very, very close.
Probably.
Actually, yeah, because we had about the same.
Well, the weather was beautiful.
It was, I know. I was because I was thinking like as it got closer, this is actually going to happen, and I'm going to see it as opposed to like
Yeah.
yeah.
It's great because all the clouds were at the edge and like everything
Right.
above you was just
Yeah, the clouds were just positioned to turn a nice shade of orange-red during totality. It's like, thank you. This is how you're supposed to behave. Yeah, it was unbelievable.
It was great.
Yeah,
An apology for the last time that
I
you
think it was. I think it was.
Were there people driving in the opposite direction again?
No, but I wouldn't have seen if there were.
Yeah, there were people driving during the eclipse.
Were there?
Yeah, because I was like right next to the road and there were like people passing out. Like it's right there.
Gosh, it's like world before swine.
Oh.
Yeah, Dr. Hankerson, who we ran into in Bowling Green, because they were in that area too, like the day, I guess it was 2 days before, we're going out to dinner, and we just randomly ran into them, basically. It was the day before. Anyway, she came down to my office today, and she knocked on the door, and she just said she just wanted to talk to somebody else who saw the eclipse, because she finds herself looking at people and just feeling pity for them now. So, you got to see a total eclipse.
One day.
Yes.
Yes, it's really amazing.
It is. 2024, that's right. Yeah.
It's all being
Oh, well,
Oh, yeah.
My backyard in 2024 will get 2 minutes and 41 seconds of totality, which is as long as this one got. However, given the high probability that on April 8th my backyard will have cloudy weather, we're probably going to be like in Texas or something.
Yeah,
So,
yeah, it'll be really cloudy.
yeah. Zach had a good idea. This is all on the video. Zach had a good idea, which is the Indians ought to schedule a game for the eclipse. So like either after the game, everybody watches the eclipse, or they just stop in the middle, because you have a whole stadium.
They should turn out the lights in the stadium.
Oh yeah.
Whole stadium go black. That would be super cool.
Well, you basically keep the lights from coming on, because the eclipse would be like 3 in the afternoon.
Oh, yeah. Never mind.
I was going to say, you're going to so much robbery.
So you saw people driving.
Yeah.
Never mind. Okay, I'll just hold my tongue. Anyway,
Explain it with math.
yeah, explain it with math. Yeah.
Proof mathematics.
Intelligence.
As intelligence approaches negative infinity,
Yeah.
the limit does not exist.
Yeah. Yeah. Okay, anyway, where were we? Is this the next thing to do? Yes, okay, so let's write the equation of an ellipse in polar coordinates. Let's figure out how to write that down. Yes, indeed. So if we go back to our figure again from before, I'll just basically redraw it here. Then there's r and r prime again, there's angle theta. Notice that this distance right there is what in terms of r and theta? So I just dropped a perpendicular there to make a right triangle. That distance is r sine theta. Yep, that's r sine theta. Whereas that projection right there is, yeah, along the bottom there. That's our cosine theta. Right? And then from the middle of the ellipse to either focus is AE. So between the foci, that distance is 2AE. So from the right triangle, which has r prime as its hypotenuse, this guy right here, r prime is the hypotenuse, drop down here, go back to f prime again. From the right triangle with r prime as hypotenuse, we have that r prime squared is equal to r squared sine squared theta. So that side right there is r sine theta. So some of the squares of the sides, r squared sine squared theta. And the other side is 2AE plus r cosine theta. So we square that too, add them together, and they add up to r prime squared, just the Pythagorean theorem. So if we apply, if we expand that second term there, one of the terms is going to be r squared cosine squared theta. So we will group that with the sine squared theta term there. So we'll get r squared times sine squared theta plus cosine squared theta, from the fact that one of the terms on the right is r squared cosine squared theta. And then to that we will add the other two terms from the expansion, namely 4a squared e squared from the square of this term. And then when we add the two cross terms, we'll get 4ae r cos theta. So plus 4AE r cos theta. But of course, sine squared theta plus cosine squared theta is equal to 1, no matter what theta is. So that's a nice simplification. So this says r prime squared is equal to r squared plus, and then let's factor, we've got a common factor of 4AE in that second piece, 4AE times the quantity AE plus r cos theta. Still on the boat with me? All right, let's keep on sailing then. All aboard. Yeah,
We're gonna have a nautical theme,
That's-
astrophysics lab.
that's right, yes. We're going to navigate with the stars.
I'm gonna get you a ship captain's hat.
Cool.
Yes.
All right, let's do it.
There's only 3 of us, we can all dress up.
We should all look at some costumes.
Yes. And then I can say something and you can be like, thanks, Captain Obvious. Yes. Now, r plus r prime is equal to 2a. So therefore, r prime is 2a minus r. Therefore, r prime squared, which we have on the left over there, r prime squared is itself equal to 4a squared minus 4ar plus r squared. Just by squaring 2a minus r, that's 4a squared minus 4ar plus r squared. So you could substitute that over there. It becomes 4a squared minus 4ar plus r squared is equal to r squared plus 4ae times ae plus r cos theta. So the r squareds cancel out. They go bye-bye. And meanwhile, 4a squared minus 4ar, of course, factors into 4a times the quantity a minus r. And that's equal to 4ae times ae plus r cos theta on the right side there. So now we divide through by that common factor of 4a, and we get a minus r is equal to ae squared plus er cos theta. So I've gone ahead and distributed through the e that's left over and multiplied it by the ae and the r cos theta and separated the two terms. And then we can arrange this then into a times the quantity 1 minus e squared is equal to r times the quantity 1 plus e cos theta. So bring the a term on the right over to the left, bring the r on the left over to the right, and factor. This gives us what we want, namely, to say that we're trying to write the equation of the ellipse in polar coordinates is to say we want to know what is r as a function of theta as you move around the ellipse. Well, squared divided by 1 plus e cos theta. So that is the equation of the ellipse in polar coordinates. So the idea of how you would actually apply it is that you would put the focus in question at the origin of your polar coordinate system, because note that r is the distance from the focus that we're referencing here. So you put the origin of the polar coordinate system at one focus, pick one of them to do this with. And then for each value of theta, you'd step around. You could imagine there's a bunch of values of theta, polar coordinate axes, right? You have a bunch of lines through it for different values of theta. And what you would do is for each value of theta, you plug into this formula and figure out how far along that direction to plot a point. And if you went around the whole ellipse and did that, you would, if you went all the way through 360 degrees, you would find that you managed to plot an ellipse as a result. So you get something where you'd be plotting for these different values of theta, and you'd come around and say, oh, looky, it's an ellipse, when you're done. So that's what it means to say that's the equation of the ellipse in polar coordinates. There's this theta, and that theta, and that theta, and that theta, and that theta, and so forth. Of course, you do it for arbitrarily many thetas, and in fact, an infinite number of them, but that takes a while. You get a nice smooth curve, that's it. So that's what it means to say this is the equation of the ellipse in polar coordinates. Any questions? Still on the boat? All right, then we will keep sailing. Now in my head, like, in the town, where I was born.
Okay, some sailor tunes going on.
That's right, yes. Lived a man who drew ellipses. So, continuing on our assumption that we're drawing planets' orbits around the sun, so that we talk about perihelion, closest to the sun, aphelion, farthest from the sun. For Earth, it's perigee and apogee. And so there's generic periapsis and aphapsis, but with the sun, we say perihelion, closest distance to the sun. Aphelion, farthest distance from the sun. We'll write down the perihelion and aphelion distances. From the same figure over there, the distance of closest approach to the sun. That's the one we call perihelion. Is R sub p, we'll use that notation, R sub p is A minus AE, right? Because if you're on, I guess I'll just keep redrawing the figure because you can't draw it too often. So closest approach is when it's right there. So if I kind of like, oh, that sucks. There's the sun right there, okay? Perihelion is one of the planets rounding the bend right there. And so the sun's at one focus, there's the other focus. That whole distance is A from the center of the ellipse, but it's AE to the sun. So how far from the sun? A minus AE at that location. Or as we would normally write it, perihelion distance is A times quantity 1 minus E. Well, the maximum distance from the sun which we call aphelion, aphelion, advanced placement helium, well, that's going to be RA, I should say. RA is A times 1 plus E, because over yonder on the other side, then you are adding, from the sun, you're adding AE to A in that case. Right? In other words, this is A over here, and AE to get to the middle of the ellipse, so it's A plus AE in that case, or in other words, the aphelion distance is A times 1 plus E. Okay, 2, 4, 6, 8. It's now time to gravitate. Time for gravitation.
Better than integration.
What's that?
I said better than integration.
Yes. Gravitation. There's something very attractive about this concept.
Yeah.
Sometimes, though, it can get kind of heavy. And in extreme cases, it can really warp your brain. Yeah.
This is when the camera breaks.
That's right.
They're cracking the lens.
I didn't think the glass could crack. It looked pretty good. Yes. The camera commits suicide.
It just falls off the table.
That's right.
Oh, God.
There goes the master of physics past. I've spoken.
Yes. M1. M2. Line between M1 and M2. Gravitational force vector on M2 due to M1. And we will use notation where that is F21. The force onto exerted by 1 shall be F21. As opposed to the equal and opposite force exerted on 1 by 2, so that's F12. F12 is minus F21, that's third law. We will also talk about R hat 1, 2, which is a unit vector pointing from mass 1 to mass 2. And R hat 2, 1, its opposite, the unit vector which points from 1, what am I trying to say, from 2 to 1. So F12 there, just to write it out, is force on M1 due to M2. That's our notation. So Fij is the force on I due to J. So our notation will be with no arrow on it. R12 is the distance from M1 to M2. Equals R21, distance from M2 to M1. R12 hat, as I've already said, is the unit vector from M1 to M2. So that will equal R2 minus R1 over R12, where R2 and R1 are the position vectors of the two masses. Remember that the position vector of a particle is the vector that connects it to the origin. So in other words, if I had some Cartesian coordinate system hanging around here, x, y, z, and here's our two masses hanging in space, then the position vector of R1, the position vector of M1 is R1. It's literally the arrow connecting the origin of coordinates to M1. Likewise for M2, there's R2. And if I were to draw, it's like we're doing the same things in E and M as we are in astrophysics. Yeah. And you did at one point. So this would be right here, R2 minus R1, right, is the arrow that connects M1 and M2. So the unit vector would be that divided by its length, but its length is the distance between the two of them. And so therefore, R hat 12 is R2 minus R1 over the length of R2 minus R1, which is R12. Another way to put it would be that it's R2 minus R1 over the magnitude of R2 minus R1. And in fact, a unit vector, you can always construct a unit vector from any pair of vectors by subtracting one from the other and then dividing by that magnitude. Right? Or basically, any vector you can construct a unit vector from it by dividing by its magnitude. Newton's law of gravitation says F12 is equal to big G times M1, M2 divided by R12 squared times R12 hat. And that F21 is obtained by just reversing the order of the subscripts. G times M2, M1, but that is M1, M2. R12, I'll go ahead and put R21 squared, but that is the same as R12. The real difference is in the unit vector. R21 hat, which points opposite in direction to R12 hat. So F21 is minus F12. As required by which of Newton's laws, which is the one that says that if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. That's the third law, yeah. So gravity, this Newton's law of gravity satisfies Newton's third law. It's built into Newton's law of gravity that it satisfies Newton's third law. This can't really be right because it implies that the instantaneous positions of the two bodies determine the force on them. But what if I wiggle one of them? Then Newton's law implies that that would instantly cause a change in the force at the location of the second one. Can that be true? No, because no influence can travel faster than the speed of light. Right, so this can't be right. It's not right. It's only an approximation. Newton was worried about the fact that it implies action at a distance, that somehow the bodies know that one another are there, even though they're not doing anything to communicate with one another. Now we know they do communicate with each other. If you did jiggle one of them, it would send a ripple through space-time that would propagate and transmit the fact that it had changed its position to the other one. In other words, general relativity is the modern description of gravity. But we won't get to that for a while. Sorry, DA.
It's small.
Yeah, that's right. Now G here is the gravitation constant, also called the universal constant of gravitation, because as far as we know, it's the same everywhere in the universe. And it's equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And notice with those units, when you plug into the formula, you get newtons back in the end. So it's not in fundamental units, right? You could turn newtons into kilogram meters per second squared and make it more fundamental units. But it's better to think of it as Newton meter squared per kilogram squared, because then the M1, M2 is kilograms squared, which cancels the kilograms squared. The units of G, the meters squared are canceled by the units of R12 squared there. So you're just left with newtons when you're done. So 6.67, it's not too hard to memorize that. 6.67 10 to the minus 11, or in other words, 2/3 times 10 to the minus 10 Newton meter squared per kilogram squared is the gravitation constant. Okay, so everything follows from this law, so we're done. We don't have to do this.
Oh, I'm sorry, sir.
No problem. Come learn astrophysics. You don't want to?
I'll see what I want to.
Well, I was thinking it was a lacrosse team. I was in here once. So I was just like, all right, you ready? So I just started.
Sure. That's what it's good.
Yeah.
Can anyone tell me what this equation is?
Yeah.
Yes,
Schrodinger's.
that would be no, sir. Yes.
So, does this one like?
I thought this was.
There's so many parameters.
We also fully consider.
Typically.
Gravitational potential,
That's so much of it.
energy. Here's a coordinate system. Here is some cute little particle that follows some sweet little path, starting with respect to this origin, with respect to the origin of these coordinates at some initial position vector, r sub I, ending at some final position vector, r sub f. Here it is, here is some little mass m undergoing this flight between them. There's a little displacement dr along the path of the particle. You can think of the path of the particle in the limit of all those dr's lengths going to 0 as a bunch of little dr's, little displacements along the path. And there's some force on that sucker. Just for definiteness, we'll say that it's a gravitational force. It doesn't have to be. It can be generically any force you like. So there's some big mass m attracting our cute little mass m. So there'll be some gravitational force on it that points towards big M. Right? Gravitation is an attractive force, as you see from the figure over there, and from the way the unit vectors play into the formula there. So there's the force on the particle, and again, it doesn't have to be towards the origin. This applies to any arbitrary force, whatever the force law is. What we're really after here is the work done by a force F acting through a displacement dr is dW equals F dot dr. That's the definition. The work done by force F acting through displacement dr is dW equals F dot dr. That's the definition. dW by definition is F dot dr. Franklin Delano Roosevelt. Oh, that's right. Your double major comes here.
Wow.
Yes.
Oh,
I feel sorry for him. You have to take it.
FDR really doesn't work. He was actually literally work. That's what he was.
That's right. Exactly.
He was defined as work. I can prove it mathematically.
He said my policies work by definition.
Hey, my policies will work.
Yes.
Where I am.
Diego's cringing at everything we say.
That's right.
He's cringing.
yeah.
The camera is not long for this world. Yes. So, what's the new deal here? Don't work.
That's true.
Not that the standards are very high.
We're setting the bar pretty high for the rest of the year.
Yeah. As it travels from its initial position to its final position from our is W will be add up all the dW's, the integral from Ri to Rf of f dot dr. Which will be the integral from the initial time to the final time of, well, force is mass times acceleration, or in other words, mass times rate of change of velocity, or in other words, m times dv dt. So m dv dt, or that's the vector dv dt, the acceleration dv dt, dot, well, dr is the velocity times the little dt. You're moving a velocity v for time dt, you go a distance dr equals v dt. So it's m dv dt dot v dt. Pull out that m, because it's a constant, the mass of the particle, pull it out. M times the integral from Ti to Tf of d dt of 1/2 v dot v dt, because d dt of v dot v, well, you can use the product rule on dot products too. So it'll be, if the time derivative of a dot v is the derivative of a dot b plus a dot the derivative of b. You can do that with dot products too. So this will be dv dt dot v plus v dot dv dt, or in other words, 2 times v dot dv dt. So these are the same thing, because here we've got dv dt dot v, here we've got half of 2v dot dv dt. Those are the same thing. So that's how we turn this expression into this expression. We're just noting that dv dt dot v is the same thing as ddt of half v dot v. Does that make sense? Any questions about that? What are you not happy with?
Not sure.
Where you buy that, I can use the product rule.
Yeah.
Okay? So the derivative of v dot v is in fact derivative of the first times the second, dot the second, plus the first dot and derivative of the second. That's all I've done there. And then that's well, these two terms are identical because dot products are commutative. A dot v is b dot a. So both of these are equal. So these are 2v dot dv dt. That's what I have over here is v dot dv dt without the 2 in front of it. So this 1/2 takes care of that. So this becomes, so d dt of half v dot v is half of 2 dv dt dot v, or in other words, dv dt dot v. I'll just write this in the other order, because that's how I have it over there. 2 dv dot that. So they're equal to one another. Well, v dot v is the magnitude of v squared. It's v squared, velocity squared, because any vector dot itself is the square of its magnitude. Because you get v times the magnitude times the cosine of 0, because there's no angle between a vector and itself. So this is m times the integral from the initial velocity to the final velocity of d of 1/2 v squared, because here I can sort of cancel the dt's if you like. In other words, ddt of half v squared dt is d of 1/2 v squared, using bad algebra but good calculus, as it were, canceling differentials. Well, the integral of the derivative is the function. So the integral of d of half v squared is half v squared. And I plug in the upper limit and the lower limit and subtract because it's a definite integral. So this gives us 1/2 mv final squared minus 1/2 mv initial squared. Anybody got a name to give me for the quantity 1/2 mv squared? Kinetic energy, kinetic energy. In other words, it's the final kinetic energy minus the initial kinetic energy. This is saying the work done is equal to the change in the kinetic energy. In other words, we just proved the work energy theorem. Ooh. Yeah. That's delta K, the change in the kinetic energy. So when next we meet, we'll define the potential energy to be minus the work done for a conservative force, and then you get conservation energy.
Down.
Bye-oh. Down.
So it's okay with switching the balance from T's to D's?
Yeah, we've done a change of variable, in other words. We've changed variables, and when you do a definite integral, if you change the variable, you also have to substitute for the limits. So that's essentially what we've done here, is if you have dt, then you have to integrate from the initial value of t to the final value of t. If you change variables to v, you have to integrate from the corresponding, the v at time ti and the v at time tf. So what we've done is essentially, implicitly, we've done integration by substitution here. And when you do that, when you change variables using a substitution, you have to also change the limits correspondingly, and that's what we've done there.
Little calculus.
Yep. Mm-hmm. D.
Eight.
I guess I think first, I don't know.
It slowly creeps up into the calculus.